All right, let's start. So there was a question from one of the students about the task 12. So I will just explain it so everybody knows what the question was and it may help. So the question was because the task 12 has some examples, like for example, eval 1, and then eval 1 only does certain tokenization. So it kind of only works for certain things using the step 1 function. And those are sort of implemented and they kind of give an example. And then later on, there is a task for you to extend. And it says, for example, extend eval 1. And then you have to implement it with additional thing like minus or something extra. So then the question is, should you do it here or should you do it there and then you reuse that function here? And it's either way, like it doesn't matter. Like if you already implemented it over there, then you can just here say eval 1, blah, 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 right? But if you haven't, then just copy the part that works for whatever it works and then extend it with the stuff that you need to extend. If it already works with the extra things, then you can just reuse it. It doesn't matter where you place it. The original idea was that you will kind of copy and paste here what you can and then extend it, but you don't have to do it this way. If you already changed it kind of earlier, okay? So that's one question regarding task 12. There was a task, another question for task 11. And in task 11, where is the code? So for example, in board tests, this test here asks you to test for a valid move, for a move out of bounds, and for the move which is occupied. And you will kind of realize, hopefully, that you can't really test occupied. So it's like, yes, great, you found kind of a situation where you have to change something, right? So what would be the natural thing to change? So you should test occupy, but with the current structure, you can't. So then think, okay, so what do I need to do? Like, what do I need to change such that I can test occupy, okay, occupied cell? It wasn't intentional, like it actually is a bug on my side, but I think it's a nice like learning experience that you actually have to think like, okay, I can test valid move and out of bounds easily, but occupy I cannot test. So what can I have to change such that I can test this case as well? You can say, okay, I couldn't test occupy, so I didn't, which is one option, but it's a little bit not that great because then you have a test which doesn't test the situation where a cell is occupied. And that is actually the value of a test. Like, you know, out of bounds and like a legal move is kind of an easy cases, but being occupied, that's the thing that you actually have to have correctly implemented. So think how you would need to change, like what here you need to change such that you can test the occupied cell, right? All right, do you have any other questions about task 11 and 12? If not, then we will go to Rust. Yay. You will miss Haskell after we go to Rust. I always miss Haskell if I go to Rust because it's such a much more intense symbol ratio to content. You have to read much more stuff and you have to like process with your brain much more stuff. Anyway, we're gonna go to Rust. What's gonna happen is, let me check the calendar. So let's. So we have today is so we have 18th, then we have 25th, and then um we have 1st of April, which we are not here, right? 1st of April is not, it's free already, right? I hope so. So then we will have day off, and then we have 8th of April. And on the 8th of April, I will announce that we have an oblique which is done in the class, and it's for the Rust. So it will be like one kind of small task to be done in the class on the 8th of April. So you kind of know that you have to come. Is it okay? Like, are people going for Easter? Everybody will be back on the 8th? Okay, I will make an issue. So if some people are not back by 8th, then we do it on 15th. But I prefer to do it on the 8th. So we'll have one extra oblique, which is for Rust, and it will be like just done in the class. So that's the plan for, but I will make an announcement on the issue tracker. Okay, so let's talk about Rust. So first, some questions. What is causing you the most trouble in C++? Like if you were to, yeah, segmentation faults. So memory management. Yeah, we have a language which gives you a lot of power, but you have to manage memory yourself. So you have to make sure that you don't do stupid things. The latest standards in C++ are helping. There is a lot of automated reference counting built in. And if you use the smart pointers, you can kind of program in a way that sort of helps you to do a memory management correctly. But still, it is something that you have to think about. Segmentation faults, yeah, that's how you start. You write something, and at some point you have a segmentation fault, and you scratch your head and you say, "What the hell is going on? Where is it happening?" And you have to find it. So a related question is a stack trace. So what is a stack trace? Who can like tell me what stack trace is? And why we care? Come on, in any language, like what is a stack trace? Online people, you can write or tell me. Anyone in the class? What is a stack trace? So first, what is a stack? Yep, very good. So when we're running a program, our own stuff. So if this is RAM, so this is our memory. Um, and then operating system and some other things are taking some space. And it's like it's a very abstract view because actually it is quite there is a lot of holes here. But let's say that we have kind of a so this is occupied, and then we have some sort of a continuous memory block which is free. So this is free, and then from the bottom of the memory, we also have some things which are occupied, and then from here we have some free memory. So when we load our program kind of goes here, in this area, and then our program says we need some constants. We have some symbols and with some constants, and all of this like read-only stuff kind of gets attached here. So our program, which is also read-only, kind of sits here, and we have all the instructions, and then some of the symbols live here. Yeah, we have to make this one smaller. And then we have a certain amount of memory, which is pre-allocated for the running program to use for passing variables from function calls and for putting a function call frames onto that area, right? And this area here we call stack, and it is because we're putting stuff on top and we're picking stuff from it. We cannot kind of access it at random locations. We have to put stuff on and then take stuff out. So it's like it is literally a stack, and it grows towards the lower memory addresses, right? And then this area here we call heap. So here we say, yeah, you can allocate, you can do malloc, you can do new. So you get some memory chunk every time you allocate memory. And this memory we call heap. And this is usually quite large. This one is usually quite small. And this one is random access. We can access anything we want. And this one is not random access. We can access only the thing on top. And then we can say, yeah, drop the top element, and then we can access the next one, right? So in very short, brief kind of a summary, a stack is part of the memory which kind of grows towards the lower memory addresses, and it's like queue because it's the last in, first out, right? So the last element that gets added to the stack is the first element we can take out. So to take this element out, we have to consume all the elements which are on top, and then we can take this one, right? And the stack is used every time we're making a function call. So every time we're making a function call, we have to put on the stack kind of a call frame, which is for our previous function. So if I have a function 1 and I have a body of this function, and at some point this function calls function 2, right? And function 2 body is here, and it does some instructions. So like a equals a plus a, and this one is doing some other things like b equals something, but at some point this function makes a call, right? So then before this call can be executed, before the control goes to this function and starts executing this function, all the variables and the state of this function it puts on the stack, and then we are pushing the control to function 2, and we start executing this thing until the return. And then once this function calls return, we close it, and then we pick this frame, instantiate it again, and jump into this point and continue from this point onwards, right? So every time we're making a function call, we have to put the previous function that we were in on the stack. And if this function calls F3, then this function is put on top of the stack, and our stack gets kind of put all the functions on top. And if we are doing recursive calls, you can imagine this like goes really quickly kind of into the limit, because we're calling ourselves if it is not the tail recursive function, right? So then when function returns, the frame is taken out, and then we go back to this function. If this function calls return, we take this frame out, and so on. So this is a stack, and this is the function tower of who called whom, right? And a stack trace is if one of those functions, let's say we are in F, 1, 2, 3, 4. So we are in F5, and this function blows up, it panics. Then what happens is we look here and we say, okay. So this function blew up. So you get some error somewhere, like line number, I don't know, like if you have the debugging symbols built in, you will have a line number of where this function blew up. But then we can look here and we can say, yeah, we were F4 also, line number 264. And this one was in F3, line number 16 and blah, blah, blah. So we can kind of go backwards and see who was the original caller, and then what this caller called, and what this caller called, and what this caller called, and then what this caller in which line called us for us to blow up, right? So then you end up with this kind of a nice stack trace, which is like this long list of functions, who called whom, when, before this blow up happened, right? Correct? And you have it in Golang. You can see that in Golang, and you can see that in C++ if you compile it with the debugging symbols in. And this situation of printing the trace of where we were in the call graph is called stack trace, right? So you should know it. Who knew about this, but you couldn't say? Yeah, good. So now you should be able to kind of explain it, right? Stack trace when you track the top of the stack. Yeah, so you basically tracking not only the top, but you kind of know what frames are on the stack, and you can kind of present it in this sort of a nice error message. I mean, we don't like stack traces, but they really help us to debug of what went wrong. Okay, lambdas in C++, yeah, the syntax is a bit wonky, so it's a little bit tricky to use, but the concept is like pretty straightforward. All right, so then what causing you most trouble in Golang? Error checking. Yeah. So Golang is quite a simple language. It's designed to be simple. It's designed on purpose to have a very explicit error handling. And the designers are really, they really like this constant error checking. But it's not very expressive. So you feel, sometimes you feel that you have to type a lot of mundane code, which could otherwise be nicely expressed as a generic code. And you cannot kind of express some of the abstractions that you would like to express. So it has certain limitations, but it is designed to be super simple and very verbose, which is a balancing act, right? So some people really like that, and they kind of don't need this more expressive abilities. But for some problems, it's very limiting because you have to be very verbose. So this ability to kind of think in a certain way and be able to express it in the language in Golang is a little bit limited. So yes, we have to write a lot of lines, and we have to do very explicit error handling. And sometimes we would like to handle errors in a certain way, but it's kind of really difficult to do. And yes, avoiding cyclomatic complexity can be challenging in Golang because of its nature, because it's very verbose, and you actually have to put a lot of lines of code into the logic that you want to express. But none of you mentioned like memory management, right? And that's super nice. It's super nice in Golang that you don't have to think about memory, and you don't have to think about segmentation faults, right? That is like a huge advantage in terms of safety and in terms of error prone, solutions. But you don't have a full control over the memory neither. You have some control of how you manage memory, but not full control. So then Haskell. Yeah, so many of you are struggling with syntax. So I think so if this is on this chart, we have like how, so let's say annoying or hard something is. And this is time. And for Haskell, of course, it's very unfriendly syntax because you are biased by all the syntaxes that you already know. So you start kind of here, and then you sort of are annoyed, and then once you get familiar with the syntax, the annoyance kind of goes really down because the syntax is very clean, actually. Like, objectively speaking, Haskell syntax is very clean. And then your annoyance with C++ or Rust is kind of, it starts probably somewhere here because you sort of know C++ syntax. And then over time, as you learn Rust features, it kind of goes higher because, so this is for Rust and this is for Haskell. Because you learn more and more features and more things that you can use in the language, and then you have so much clutter in the actual syntax that you stop liking it. Like you have a lot of mental difficulty reading all of this because it's so dense. Like this one is very thin. Like there is not much actually happening in the symbols. Like, you know, you have to learn how to read this, how to read the dot, and how to read those few symbols. And then once you kind of understand this, there is no clutter anymore. With Rust, this list of symbols that you have to learn with all the ticks and all those things that are kind of coming in and all the dot functions, it's kind of infinite. Like the complexity here is so much bigger than here that at some point you will say, yeah, I reached that point. I kind of, I'm like starting to like Haskell and now I'm stop liking Rust, okay? This point in time may not happen this semester. So like give it time, right? But it will happen. So syntax, yeah. But apart from syntax, so some concepts are kind of harder. And the kind of fun thing is that the concepts are kind of very similar, like both Rust and Haskell on the concept side. They kind of are very compatible. They use a very alike concepts, but Rust is a little bit handicapped. So Haskell has similar concepts to Rust. Rust is borrowing a lot of concepts from Haskell, but Rust makes them a little bit handicapped. They are not as powerful as they are in Haskell. So Haskell is like a superset, which has everything, and it has everything kind of like really well done. And Rust takes some of this and makes it a little bit like constrained, which makes it probably for some people a little bit easier. But at the same time, people who know the concepts already, they feel limited. Like, you feel like, why I cannot do this, right? So they are kind of similar. Managing state, yeah, in Haskell takes some time to get your head around. Folds are a concept that is universal. You may find folds in JavaScript, you may find folds in Rust and other modern languages. So understanding how folds work is a little bit universal. It's not unique to Haskell. Syntax, yeah, I get it. But imagine that you never learned programming and the first language you are learning is Haskell and you don't know any other syntax. You're just learning that syntax for the first time. Then you would basically start here. Haskell syntax would be to you as normal as C++ syntax, and then you would kind of stay on that level, like from the very beginning. The reason why you hate this syntax is because you started with C++ syntax to start with, right? And there were actually some studies, and the studies suggest that people who, so it was kind of like this. So again, how hard something is. So, and then what people, and this is like categories. So if you started with C++, and then you are learning Haskell. So then people say, okay, Haskell is very hard. So Haskell is hard for people who already know C++. And then for people who are starting with Haskell, they say, yeah, Haskell is kind of not that hard. And then, so this is Haskell. And then for those people learning C++, kind of is like this. And then for people who already know this, then of course it's kind of like we already know it. So like you say, yeah, that's kind of easy, like, you know. So C, C++. So for people who've never done any programming at all, they like learning Haskell first, then learning C, C++. And there was sort of recommendation that maybe if you're teaching programming, you should start with functional programming first, because then people are not biased by imperative programming, and then they acquire the concepts much easier, and then you can do the imperative programming afterwards. But we sort of don't do that, and even though the evidence suggests that that would be easier for people to go through, that like C, C++ should have come after initial functional programming. But yeah, you have it the hard way. You've learned imperative programming first and so on. I did the same. So for me, Haskell was also hard because I've learned from assembly and imperative programming and then went to functional afterwards. And it is harder. All right, so then why we study the C, C++, Go, Haskell, and Rust? Why we study those languages? Yeah, so very, very good answers. We want to learn different styles. As we've seen from the previous answers, some languages have certain strengths and certain limitations, and we want to know the spectrum. We want to know what the languages feel like and what strong and weak spots they have. We want to learn like what they have for us to offer. We want to yes, be exposed to multiple things, and also the nature of the language kind of limits the way you solve problems. And then there is always a perfect tool for the job, and it's not like there is one language or one framework which solves everything. You always have to find balance, and you always have to find some trade-offs. So yeah, to be adaptable. So I was sort of learning some languages. I've learned a couple of languages, like maybe 4. And then I read this paper, which we have on the wiki, which says 700 programming languages. And in this paper, the guy says that currently on the market, there is about 500 languages which are used around the industry. And that was written in 70s, okay? So you can just imagine how many languages are out there and you're not aware of them, right? But most of them share certain common characteristics. And if you know those characteristics, using those languages will actually feel not that weird because you already were exposed to the concepts. And we picked those because those are the most kind of relevant. They are widely used in industry, with the exception maybe of Haskell. And Rust is also a little bit of a niche at the moment. And they kind of expose you to a variety of things. They are all compiled languages with a strict type systems, and they are very suitable for writing software in a variety of domains and also for long-running software. There are languages like, like specialist languages, and one of the specialist languages is JavaScript or TypeScript. It's specialist because it usually fits into the front-end web development. Although with the Node.js, you can do some backend or service programming, especially with cloud functions. So there is, again, but it is kind of, it's not a general purpose language. It's kind of a specialist language, right? And then we have languages like Python. So Python is also a specialist language. It's a scripting language. and it's designed usually for writing kind of ML pipelines. Can you do kind of a general purpose stuff in those languages? Yes, they are Turing complete. They are equivalent to other languages, but why would you? Like, what would be the advantage of doing that in those languages rather than those languages? Well, one of the advantage is rapid prototyping, right? So if you need to rapidly prototype something, then some of those dedicated scripting languages are actually very good for a quick iteration over an idea. They are quite fast in prototyping stuff because they don't require a lot of structure, and they are kind of easier to hack something together, which almost works. But then if you need something that is like long lasting and maintained for years, then those languages show up the deficiencies, right? So strictly typed languages kind of over time, they won basically. Like we know that maintaining something that does not have a type system is a nightmare over time, right? And you can see that with Ruby on Rails or some PHP systems. They tend to be like a security nightmare. And so, for example, we have GitLab. GitLab is written in Ruby. Ruby is a very nice language, but it does not have a proper type system. And Ruby on Rails framework was like advertised in 2000s as a very nice framework for doing web apps. But like it turned out to be like extremely slow. And like GitLab is extremely slow because it's written in Ruby and really difficult to maintain. So the number of security vulnerabilities and the number of patches they have every single week, it's like enormous, and like you have to continually work on it. So you've built a product and now you have to spend full-time job just like patching it and making sure that it doesn't fall over, right? And that's ridiculous. So maintainability and like the performance is like really, really bad. So why would you do that? Right? Why would you implement it in the language which makes you work much, much harder, right? And JavaScript is the same. So those languages here are kind of very similar and they have similar characteristics. So yes, they are used, and yes, you can rapidly prototype something, but they rapidly prototype the initial GitLab and now they got stuck. Like rewriting it into something else is like a major financial undertaking, and they are not going to change that, right? All right, so one more aspect. What is system programming? What is systems programming? Yep. Programming systems, low level, bare metal, assembly. So there is a whole hierarchy, okay? So at the very bottom, we have a very, so if the metal is here, then we have certain things which directly touch metal, okay? So what really touches metal? Drivers, so drivers, hypervisors, OSs, maybe some even like maybe some subsystems for running stuff inside OSs, right? They also are kind of very low level, right? So all of this is very low level, right? Then we have a layer which is the more kind of a so we have a kernel facing and we have a user space facing part of operating systems, and they are a little bit above because they don't talk to the metal directly. They talk to the metal through all those other components, right? And then we have certain stacks inside the OS and sometimes a little bit above. So for example, networking stack is sort of somewhere here, right? Maybe like IO, and so on. So this is all like up to that level, it's pretty low, right? We consider that like a low level. And then a little bit above it, we have frameworks, libraries, kind of compilers. We have all the kind of tools which allow people to build something, right? So all this is kind of in between. And then all those tools here are sort of used for people to build applications, right? And then this layer is also kind of, we have apps, but those are kind of a more general purpose apps. And then we have some specialization apps. So like mobile is not a like mobile desktop and so on. It's sort of a more specialized areas, right? But from around that layer here, we sort of say application development. And below that level here, we say systems, right? So it covers quite a diverse space of everything that is sort of allowing people to do something, right? So building like applications and so on. Like if you think, what do you use to produce Hello World? Like it's an enormous amount of stuff that you are using. You're using some IDE, you're using some libc libraries to print to the screen, using the compiler, the linker, you're using the operating systems with interrupts to print something and so on. So like to write, like if you are human and you're writing Hello World, you're using enormous infrastructure to be able to write a Hello World program, right? And those enormous infrastructure, somebody had to build for you. You're not building it yourself. You're benefiting from all this infrastructure that has been built for you, right? If you're making a web application, it's very similar. You have to use a browser. Who wrote the browser, right? And the browsers are kind of here. So browsers are sort of like part of the systems. It's not really an application domain. It's something which offers other people to be able to write web apps on your browser and so on, right? So the boundaries are kind of a little bit blurred and the boundaries are not crisp, but you can imagine that that this is how it looks like. And if we drew a kind of a pyramid of how many people are using something according to that stack, if this was the boundary between this kind of apps and then all the support, so the apps is like much bigger. So here is like infinite number of people kind of using and building stuff, especially if you go to some sort of scripting, like, you know, ML scripting with Python and so on. Python. Then like much more people are doing that. And here we have those C++ guys who are writing all the tools for those people, right? So for somebody to use ML in Python, there are people which are building all those libraries and so on in C++, such that those people can write Python scripts to draw charts or to train ML models, right? So it is kind of a dependency, but amount of people being here, it's much bigger than the amount of people being here. And in Yovik, we are sort of kind of like pushing you a little bit down. Like we're not saying you will be application developer. You will be writing like crude applications for, you know, a grocery shop for counting the groceries and like doing management. Of course you can do. There is infinite amount of demand for this type of applications, but we are kind of telling you that, well, we're equipping you with some of the skills which allow you to look and do something a little bit here. You can write a library or you can write a framework which will help people to build those things, right? So you are, but because then if you do something here, you're influencing kind of much bigger population. If you do an application for a grocery shop, you are maybe influencing a one shop, right? So your influence is very limited. It's like very kind of narrow, but from here, your influence is much bigger. if you make a small tool or small framework, you're kind of affecting multiple of those people doing stuff, right? So if you write a new C library for ML, you're influencing kind of a really big population of people who benefit from it, right? But the job market is a little bit different. So the job market here is a little bit smaller because there is less people needed to do all this infrastructure. But this infrastructure influences a lot of people there, right? So those languages are sort of like looking down here. If people are teaching Java and C# and like Python, you're kind of pushing them here. You're pushing them to the boundary where they will be working with the one-to-one kind of situations. If you're teaching them those core languages, you're kind of pushing them a little bit towards the lower levels, right? System programming. Again, it's very, the boundaries are not clear. And it's like, as I said, like some people write web frameworks in Python. They do it and they sometimes use it, but it's not very popular because it turned out to be not that great idea for maintenance. Creating programming languages, creating compilers, creating libraries, creating tools in general. So like being a tool maker, and for being a tool maker, you have to have this sort of ability to look a little bit lower into the hierarchy of the value chain. All right, so finally, Rust. So Rust is heavily inspired by Haskell. As I said, concept-wise, there will be nothing new in Rust that you haven't been exposed because of Haskell. So concept-wise, you already know Rust. Syntax-wise, yes, you will have to learn. It's memory safe, but it uses a different concept for memory management to the systems that are runtime based. So how to explain it? So typically, if you have a language and you have to do memory management, you have two places to do it. So the classical kind of approach was C, C++, and then that means here is a human, and here is the computer, a runtime system, or often garbage collector. So in C++, we say, yep, the human will be allocating and deallocating memory, and the responsibility is on the human, right? And then all the other languages, so everybody else was saying like, including, so everybody else, including Haskell, Golang, what do you have? Java, JavaScript, Python, whatever, like everybody else. Everybody else was saying, okay, it's the responsibility of the runtime system to manage memory for the user, for the programmer, in such a way that the programmer, when they allocate stuff, the runtime system will keep track of what was allocated and it will clear the garbage when it's not in use anymore, right? So that was the picture before Rust came about. And in C++, as I said, initially with all the initial standards, the human was doing everything, but now it's a little bit like it's a small tick on that side, because if you use smart pointers, then the runtime system do some reference counting and will deallocate stuff for you when something goes out of scope. So if you're using a smart pointer which goes out of scope and you're doing it kind of using some of the latest standards, like from C++ 11 onwards plus, then you can benefit from some of the safety checks and some of the mechanisms which are actually on the runtime system. They don't have a garbage collector. No, there is no garbage collector as such, but there is a little bit of deallocations which you don't have to think about. It will kind of happen for you, right? But generally, it's the human which needs to think about allocations and deallocations. In some of those languages, so in Haskell, you not normally think about memory. In Golang and Java, so in those you don't think, and in Haskell you normally don't think. In Golang and Java, you have like in Java you have new, and in Golang you have make things. So you also have, let's say you have make. Then you are allocating memory, and you can allocate memory on the heap or on the stack, but you don't deallocate it, right? So you say I need memory, and then the garbage collector and the runtime system kind of manages it for you, right? So those were the two words. And then what happens is Rust came along, and they said we don't want the human entirely to do it, and we don't want garbage collector neither. So they decided to have kind of a separate category, and as far as it was developed, it is so here you have the human controlling everything. Here you have the garbage collector or runtime system, and here it's like compile time. So at compile time, the compiler will make sure that everything that is allocated and goes out of scope is released properly. So compile time memory management. Okay, so Rust is here, and Rust is quite unique in this regard, right? Because it is the role of the compiler to make sure that everything that is allocated is properly deallocated. This influences the language. So to have this memory management here done by the compiler, the language has to be designed in such a way that it allows the compiler to reason about memory allocations, right? Some people say that, at least initially they were saying that, well, it's like, yes, we can kind of do the same in C++ by static code analysis, and you can kind of run. So if you have your source code, the static code analyzer can go over the code and check when you're allocating and when you're deallocating memory, and kind of do similar thing to Rust. And initially, when Rust was in the early developments, that was true, that the difference between Rust and C++ with static code analysis was very similar, but there are limits of what can you do here. There are limits because of the language. The language does not help entirely the static code analyzers to kind of resolve all the possible situations, right? In Rust, it does, because the language kind of enforces certain rules, and because of that, the compiler can do 100% of the job, right? Here, you cannot do 100%. You can do a lot, but you cannot do 100%. So here, you can do less than everything. Here, you can do everything, right? So 100%. And it is safe, so in a sense that it is doing 100%. You will not have memory problems, because if you wrote something and the compiler analyzed it and like gave you a thumbs up, that means you memory safe. All right, so it's excellent for embedded systems and for system programming. So all the stuff which goes like below the application layer. Some people use it for application development as well, but you wouldn't write your web apps or like mobile apps necessarily with Rust, right? It's a little bit too heavy for the task. It's excellent for resource-bound systems because you have very small runtime system, because there is no garbage collector, and because all the stuff that is heavy, it happens at the compile time. The actual executable is very thin, very small. Very good for real-time systems because you don't have a garbage collector. So there is nothing influencing your execution, right? And that's why when you're doing games, you kind of usually prefer languages which are allowing the programmer to define exactly what happens and when memory allocations and deallocations happen, because you're in full control. You control exactly how things work, and you don't have like a unusual interrupt from the garbage collector saying, yeah, everybody freeze for a moment, I have to clean garbage, right? That wouldn't work with games, because you have to have a constant frame rate and you have to be predictable, like what happens when, right? So that's why Rust is very good for that. So Rust is sort of same category of problems where C++ fits, right? But it's a modern incarnation. So it is statically typed, strictly typed. There is no garbage collector. There is a compile time memory management. and there is no inheritance, and mutability is on request. So you can see the no inheritance, we talked about it. We will have one more lecture about object-oriented programming and certain features of why object-oriented programming is a little bit so when OO happened, we thought, oh, it's so great, we will use it for everything. And then over time, we learned that that was not that great idea. There are places where OO is super nice, super good, and places where OO does not really fit that well. And modern languages like Golang or Rust, designers decided that some of the OO features like inheritance have caused more problems than benefits, and they actually opted out of using inheritance, right? And Rust does not have inheritance. And then mutability on request is a little bit of a twist, because normally in imperative programming, you assume when you bring a variable into a scope that the variable is mutable. That's the default behavior. And in many languages, you can say, no, that you cannot mutate this variable, so you can enforce certain constant or certain keywords to make it kind of immutable, right? But in Rust, they said, no, actually, the default is that everything is immutable. And if you want something to mutate, you have to declare it as mutable. So they kind of turn it around such that they sort of, again, followed a little bit of a functional or maybe Haskell feel that things are immutable by design, because then it's easier to reason about it. And if something is mutable, then you have to put extra machinery to reason about it. So the default is that if you have a variable brought into a scope, that variable is immutable, right? Because that simplifies a lot of reasoning about the code. So I kind of like this. And the syntax you will feel at home initially, as I showed you on the graph. Initially, it's like, oh yeah, that's like a breath of fresh air. It's like C++ syntax, with some twists, obviously. So the twist is, again, most modern languages, they put the type after the variables or after something happens, right? So you might have noticed that with Golang. It's the same. And it's a very clear reason for this. So if you have a variable and the type comes in front, that causes a certain syntactic trouble when you read more complex things. And then if the type goes after, that syntactically, the syntax of the language is sort of much easier to compose. And one test for this is if you would like to define a function. So let's say you have a function which returns int and takes an int in C, right? No. So that is like the base case. So let's say there is a function which returns int and takes an int. And now you want to define a new function which takes this function as a parameter and returns this type of function as a return, right? And try to write it in C. And you will see that you almost want to kill yourself, right? And it is because this thing comes in front, right? This thing comes kind of here, that you are returning the function. So if we turn it around, if we kind of turn it the stuff around, suddenly writing this function like in Golang is super nice, because like you kind of say what it takes, and then you will say that it takes a function which takes an int and returns an int. And then here you will say it takes an int and returns an int. And like it's much more kind of natural to sort of have this kind of the type coming afterwards. So again, modern languages, like just try this in Golang and in C. And you will see that in Golang, you can almost do it without looking up the syntax. You kind of just can do it. In C, you will have to look up syntax like multiple times, and you will get it wrong multiple times. So they kind of have same in Rust, but annoyingly, they have to use this semicolon for defining like the type from stuff, right? when initially I was learning Rust, I was like, why do you need this? Like you can write a parser which does not need that. Like Golang did it, so it is possible, right? But they couldn't do it, so we have this extra symbol. Languages which introduce extra symbols not necessarily make it better. Like there is more visual clutter, right? But maybe that's like not too bad. Maybe this particular clutter kind of separates the type from everything else, and maybe that's okay. But I personally, I didn't like it. And then you can see this modifier, which says y is mutable. X is not mutable, but y is mutable, right? And it uses semicolon, same as everywhere else. And then you have let for declaring variables. So some languages use let, some use var, and so on. Like that keyword, you basically have to memorize. It's very similar to C syntax, and you have kind of a powerful macro language, which allows you to define some syntactic manipulations of symbols such that you get more control over your language. So you can extend the language by those macros. And some of those macros are built in. The macros are recognizable because they have a bang. They have the bang at the end of the names, right? So if you see a function with a bang, that means that's a macro. You have some resources, and you have some books, and they have all the tool chain kind of built in. They have cargo, which is the same as stack, which manages your builds and manages your dependencies. And they have the crates.io, which is the main package management web portal. And all the publicly available dependencies are managed by crates. And the best way to install Rust is to use Rust app and then keep updating when you need to update using the Rust app. So it's kind of similar to GAC app. So you can see some parallels. For Haskell, we were using GAC. What was that called? GHCH? Up. And then here you have Rust app. Those are kind of equivalent. What was the Haskell called? GHC app? Let me see. GHC app, yeah. GHC. So let's have a break. Let's have a break. All right, questions. Sorry, didn't see chat. Oh yeah, sorry about the background blur. Ah shit. So you didn't see the. Yeah, apologies for this. I didn't realized. Yeah, too late. Apologies. Yeah, I'm sorry for this. I didn't realize. You should have turned the mic on and just shout at me. So next time, please interrupt me, and then I will fix it. Yeah. No, yeah, I didn't realize this on Menti neither. Yeah, sorry. Um, okay, so whiteboard. Should work. All right. That should work. All right. So relative difficulty of languages, what do you think? There is no correct or incorrect answer. It's just your personal like feel. what do you feel? I mean, you may not practice all the languages, but the ones you practice, you can kind of answer. And if you haven't practiced a language, then you just think what you think. You just specify what you think. Yeah, quite revealing. I Obviously, this is just an average, and obviously it kind of is very personal. But as I told you, there are some studies which suggest that learning Haskell as a first programming language is actually quite intuitive for people. So there is the book. I'm not sure if it is the book that we are using in the course or another book, but there was a functional programmer who had a girlfriend, and she was not a programmer at all, and he was trying to teach her programming, and he used Haskell, and she loved it. She sort of said, yeah, that's so kind of mathematically sound and like intuitive, and she sort of liked learning programming through learning Haskell. But I think it may be true for some fundamental concepts in Haskell, and some concepts in Haskell become kind of complicated, quite hard. Um, I also agree that Python is probably the easiest, very similar to Golang. And JavaScript is kind of weird because the basic things in JavaScript are super easy, but JavaScript is also a weird language because it has this very functional flavor, and you can do a lot of twisted things in JavaScript. And those twisted things are kind of Haskell hard. They are kind of, really out there. And on top of that, JavaScript has a lot of weirdness. It has this triangle inequality, right? You can Google that. And it's like, why? Why the hell you have language which has such a stupid design decisions, right? So if you learning JavaScript, it's sort of a love-hate relationship. Like the more you dive into it, the more you start hating it. Like initially you was like, oh yeah, it's great. It's a very easy scripting language for manipulating DOM elements. And it's like, yay. But then it's like, no, it's not. It's this nightmare. And then it's like, you hate it. So I went through this. Like I fell in love. There was a period where I was doing everything in Node.js and JavaScript for about 2 years because it was so nice for rapid prototyping and doing a lot of things. But then maintaining this, it was like nightmare, and then you have a lot of issues. So yeah, like love-hate relationship, I guess. So it is a little bit, I don't have Python, but yeah, Python would be kind of around here as well. So this is kind of my take. So Rust, unfortunately, is kind of a little bit towards the Haskell scale, right? So Rust is not an easy language neither. So Haskell is by far the hardest I've learned. Okay. There are worse languages than Haskell, okay? You can try brainfuck. So try to write like A plus B in brainfuck. That's how far I got, okay? I can write A plus B and that's it. But yeah, like with normal languages, Haskell is quite out there, and Rust is sort of like it is easier, but it is a little bit out there as well. I think Go and C are very similar. I agree with you that maybe C is a little bit harder than Golang. because you can do more weird things. So according to you, C is substantially harder than Go. Yeah, you're probably right. All right, so then heap versus stack. We had a little bit of a summary before, but some of the online people didn't see it, so I will just very quickly to kind of draw it again, so the online people don't complain so much. But you have the memory RAM in your computer. It kind of ends here. This is the end of your RAM, and this is the last address of your RAM. And then this is address 0. And then the beginning is kind of occupied by stuff. Then you have some operating system and other stuff occupied. Towards the end, you also have some stuff which is kind of occupied. And then you end up with the space in between. And the space in between is shared between the stack and the heap. So heap kind of grows towards the more larger memory addresses, and stack kind of goes backwards. And then on the stack, you put stuff on, and then you have to pick stuff out. So it's like a last in, first out queue, right? The last thing you put in is the first thing you take out. And then the heap is just like a memory. You can allocate memory, you can free it, and so on, and it gets kind of partitioned. So if I allocated small memory and then small memory and then a larger chunk, and I freed the middle one, then I have like a hole. So here it's free, but those two are kind of allocated, right? And then you have some problem, because even though you have more, like quite a lot of RAM, you cannot allocate a certain continuous memory amount because it's like partitioned and so on. So there are some techniques for dealing with this. You probably learn some of this in the operating system course, but we kind of don't really think about it. We treat it as some sort of space which we can allocate, like a pool. We can allocate memory and then free it. So this is heap, and this is like stack. So stack is for the stack frames of the function calls, and that's what we discussed as a stack trace thing. But it also stores when you say, I want to call function f, and function f takes an a, which is an integer, and b, which is an integer, then those two have to go somewhere. And sometimes we can optimize it such that we have them in registers, but most of the time they have to be put on stack. And there is a special like protocol or special agreement, like in which order we putting the arguments on the stack, and then the function which gets called, which is f, will pick those arguments from the stack, right? So we're also communicating those things through the stack. Also, if this function has declarations of some variables that are local to this scope, so let's say this has an integer and a bool, or something like this, then those variables will have a kind of an allocation on the stack memory such that the program can kind of use them, right? I said this is like last in, first out, but there is like on the stack, there is also kind of a space for all the static allocations. So when the compiler compiles this, the compiler knows I need 2 slots for the parameters, which will be passed on the stack, and I need this allocation for int and for bool, which will be manipulated by this function, and it kind of allocates some of that space here, such that it's like statically pre-allocated. You don't have to like allocate it on the heap. It's kind of pre-allocated on the kind of stack area, right? All right, so heap memory. We have to explicitly allocate it and release it. And in the languages which we discussed, some of the allocation and releases is either done by the human or by the runtime system. And then we don't know how much memory you will need, because at compile time, you haven't calculated everything. And then some of the allocations may depend on what the user is doing, right? So it depends on the flow of the control of the program. So it is not known in advance how the heap memory is being utilized. So it is slower, but it's very big. Like we can work with arbitrary large allocations. And then stack, we know at compile time what is needed. We know exactly what we need, and it's pre-allocated. So the slots are pre-allocated at compile time and when our binary is loaded in memory. It follows this last in, first out methodology. It's faster, and the whole stack pre-allocation is released automatically when the function finishes, right? Because the function is taking out, the stack frame is being taken, and then it kind of is released automatically. So any questions about heap and stack? You had it right before. You've learned about this. It's just like a refresher. So stack, it's everything that you have inside the function, as I showed you. Stack is passed by value every single time, and it is contained to a single function only, right? And heap allows you to pass data across functions, but you say, yeah, but we have f, which is doing something, and it calls f2, and it passes an integer, right, to f2. Is that communicated by heap, or is that communicated by stack? Well, technically, it is communicated by stack, right? Passing parameters is communicated by stack. But if you want to pass something bigger than those pre-allocated things, or if you have something of arbitrary size, you are passing a pointer to an int array, then you may need to have the pointer pointing to heap because you didn't know what was the size at the compile time, right? So heap passed by reference. And that's also quite interesting because some programming languages like Java, Java has this concept of primitive types. So you have primitive types. And this is like integers, floats, bools. What else is primitive? Some like string literals. I think, yeah, I don't remember what other primitive types, but the usual ones is like numbers and booleans. Those are passed by value. So by value, but then everything else is by reference. You cannot pass an object by value in Java, right? It's not possible. You have to pass it by reference, right? Which is a bit weird. Like if you think about it, it kind of takes a lot of control of what can you do. So if you have a struct, which is an object in Java, you can kind of not be able to pass it by value, right? In most languages you can, like in Golang, you can. So here is a Golang snippet. So we have a struct with name and age, and then we have a function which takes a name and age and returns a student. And then it creates a student inside the function and returns it, right? That's the first version. Version 2, we are doing the same thing, but we say, no, like we have to return a pointer to a reference to a student, because otherwise this student goes out of scope, right? Like it's declared locally inside that scope. It's allocated on the stack, and it will go out of scope the moment we do this, right? So if you write this function in C and you try to use the student outside of this function, what's going to happen? So what will happen if you have this function in C or C++? What? It's not going to exist. So the moment you try to use it, what's going to happen? You're going to get segfault, right? The runtime says like, what the hell? You're touching something that does not exist. Like, why, what are you doing? You deallocated this already. So you're going to have a segmentation fault, right? So this code is illegal in C. You have to do this, right? In Golang, what happens here? Is it legal? Did you try it in Golang? You can try it. And it turns out Golang is like doing some magic for you, right? So Golang will happily say, yeah, this is fine. Oh, wait a minute, you want to return it. That will be a segfault. So we cannot allocate this one for you on the stack. We have to allocate this one for you on the heap. And then this is a heap variable, and then it's kind of returned as a value to the heap memory, right? So Golang, if you didn't have this, would allocate this on the stack, and it would kind of treat it as a local variable. But because you've done this, the Golang tries to be smart and prevent you from having segmentation fault and saying, yeah, okay, we got you. We're gonna put that on the heap for you automatically, right? Because this is like the programmer says, yeah, put this on the like on the heap because I'm kind of returning the reference to it. But this one is like not. It's like saying like, yeah, we kind of doing local thing. But Golang is kind of catching this and kind of making the substitution on your behalf, right? Which is from one hand, it is kind of nice, but on the other hand, it takes control out of your hands because you cannot shoot yourself in the foot anymore. Like you cannot do something that segfaults, right? Which is kind of nice, but at the same time, it's a bit weird because you lost this control. In C, you have it, but in Golang, you don't have it, right? So Golang manages the stack and heap allocations for you, and you don't have the full control. So in C and C++, you do have a full control. In Golang, you kind of don't have the full control. And then the memory safety is guaranteed because of this. And the runtime system kind of says, yeah, I got you. Like we're doing things that looks what you want. Like it looks like you want to pass it outside of the function, so it has to be on the heap. So the boundary of what is on the heap and what is on the stack in Golang is a little bit not tied to the syntax. It's tied to the syntax plus behavior, right? In other languages, it's very tied to the syntax. So you can shoot yourself in the foot, but in Golang, you can't. Okay, so then a quick overview of Rust. We have the typical value types. So we have tuples, structs, arrays, slices, and enum types. So those are the core concepts that you already know. The only thing that is a little bit new will be enum types, but as you will see, those are pretty familiar to you as well. So tuples, you know, I have the and tuples in Rust are kind of real tuples because in Golang there is something which feels like there are tuples, but they are not really tuples, right? So in Golang, if you have a function which like you call the function and it returns two things, which looks like a tuple, error and the value, right? Which is a very typical pattern, like your function returns two things, but those two things are not really a tuple, right? Because you cannot say, I want this to be my tuple. You cannot do this, right? And T would be equivalent to a tuple of an error and a value. You cannot do that in Golang. And again, I'm like, why not? Like that would be so nice if we have tuples, because then I could collect all the tuples from my function calls and then do something with them, right? But I cannot. I have to say the error is here, is bound to this variable, right? Not to the tuple. Anyway, like there are some language decisions which the designers kind of make. And in Golang, the tuples is a bit of a weird concept. But in Rust, it's proper. Like if you're returning two things, it's a tuple. You can assign it to a single variable. It's fine, right? You can destructure it. You can do destructuring. So you can kind of unwind the tuple into two things, but you can return it into a single variable as well. So you also can declare a type alias. So you can say, I have a new type, which is sort of an existing type, very simple. And then you have this very assembly-like, very WASM kind of type number and type system. And it's very intuitive, but and kind of concise. So you have integers, which are either 8 bits, 16 bits, 32, and so on. You have unsigned integers, you have floats, and you have bool, string, and the string literal, right? So those are quite nice, very uniformly defined. And if you're learning WebAssembly, WASM, you will see that the WASM is using the same kind of notations for numerical types. But it really feels kind of a very low level, right? So tuples are proper, not an illusion of tuples. So you can have an empty tuple, which we use often, like we just want to return an empty tuple. Or you can have tuple, which are two different things. In this case, it's a number and a string. You can compose tuples the way you want. They don't have names. So like the tuples are not a record type, but it's sort of like, so the record type is like structs. So you have normal structs with name fields. But you can have a tuple struct. So it is sort of like a tuple, but it is a struct and it does not have names for the fields. You just go 0, 1, 2, and so on, right? And then unit structs, which are just for singletons. So that's what I showed here. You have a singleton. You can declare a particular type to be a unit type. And then you just have this kind of one single instance. So here we have, so maybe I go here. So here you have a declaration of a point struct, which has two named fields, X and Y. Again, the type and the value use the colon. And then you have an empty singleton struct with no fields. And then you have the tuple, which is just two numbers, or you have the struct. So the brackets here are round, and for structs we use the curly brackets. And if you don't specify the names, it will be 0, 1, 2, and so on. If you specify the names, you have the kind of the naming for the fields. And then if you want to instantiate a struct, you're basically doing curly braces, colon, and then the values, right? So you can reorder because it's kind of indexed by the names. If you're using this one, the order is important, or you have to do this numbering, like naming thing. And we have generic functions, and then if you need to pass a type using the curly braces, and we also have this notation with double colons for referring to something that is in the scope, or for yeah, it's basically a scope thing. So similar, a little bit similar to C++. So there is nothing new really. Like you are kind of familiar with all those constructs, right? So syntax is very similar to Go, C++, and then same as Golang, Rust structs can have implementations. The syntax is a little bit different, but the idea is kind of the same. So if you have a struct, then you can have a block of functions which are implementing behaviors on behalf of that particular struct, right? So it's you will see it in the it follows this keyword implementation, and then you define functions which are doing something on top of the struct. So one concept that we have to introduce, so we already introduced like two concepts. One is heap and stack. We have to pay attention to those two. We didn't have to in Golang or in Haskell. And the other one is memory alignment. Memory alignment is what? So here we have an example where we have a struct with F64. So this struct will occupy 64 bits. And then so this is an example of implementation. So we have a struct, and then we have the impl for our struct, and then we have the multiplication function, which operates on our struct, and we have to put this self into the parameter list. But mul, when we call it, it just takes one argument, right? So when we declare it, it kind of appears it takes two arguments, but when we call it, it kind of appears it's taking one argument. But the first argument is here. So this is like a syntactic sugar, because mul takes v as the first argument and 20 as the second argument according to this signature, right? So you can see that it's like, okay, I can do it in C as well, right? You can kind of basically say my structs in C have behavior because I can write the same function which takes a reference to my struct and then parameter and then does something with my struct, right? But in C, you would call it mul v, 2. And in Rust, you have the syntactic sugar, same as in C++, where we say this dot notation. So we say, call this function on behalf of this struct with this argument. But you see that there is no real magic. It's like the struct is being passed to this function as the first argument as a reference, right? You get it? Yeah. So this is the example for the that point, not for that point. So same as Go, structs can have implementations, and the implementation is this input block for your struct, and then you have functions which have to take a reference to the struct. And sometimes you're taking the reference as immutable, so you're not mutating the reference itself. But if you have to mutate it, you have to declare I'm taking a mutable reference, right? You will see it later. And then you also see that functions in Rust follow the fn keyword, then the name, then the arguments for the functions with the type going after the variables, but not for the first one, which is always this, always the same. And it has to be called self, and it has to be a reference, but sometimes this one is immutable, which means we're not mutating that value. But if we were to mutate it, we would have to pass a mutable reference. And then we say an arrow, and then we say the return type of this function, right? And that was already my first, like, why don't you use the colon, right? We're using colon for the type. Why didn't you freaking use the colon for the type of return of this function, right? No, they couldn't do it. They have to use a different symbol, right? So you have to learn it, that like the return type follows the arrow, not the colon. Extra rule to learn, extra things to remember, and extra symbol to deal with. All right, so then we're going back to this one, memory alignment. So what is memory alignment and why do we care? So we kind of talked a little bit about it already, but not really. We sort of mentioned something. So we mentioned that if you have your heap and you're allocating stuff, so you kind of allocating array, let's say array of 2 elements, and those 2 elements is your struct, then it kind of allocates from here to here, the memory. And memory alignment is how is your utilization of the space inside your struct. So how well you are kind of packing the struct that you're using here, right? Because if you're using like this, then you're kind of utilizing those marked things, but those things are empty, you're not using them, but they are still occupying space in memory, right? So you're leaking some space that you don't really utilize. And that's a bad thing, right? So memory alignment is how data is laid out in memory, because in the computer memory, we have to arrange everything by words. So we cannot address something that is not a word. So on a 64-bit architecture, which are the dominant ones, words are 64 bits, right? So 64 bits is one word. And then we cannot address, so like if this is address n, this is address n plus 1. It is sort of at the end of the 64, right? So it kind of starts here, and we cannot address something in between. We cannot say jump to here, to that byte, or to that bit, to those 8 bits. We cannot do that. We have to say jump either here or jump here, right? So that means when we addressing stuff, and we are addressing stuff here in our array, we say you can go here, or you can go here. So that was the first record, and then we have the second one, right? So inside the struct, we can extract intermediate values. So even though I cannot address that particular thing directly, I can address this thing, but I can say the first 8 is X, the next 32 is Y, and then the last 8 is Z. And then I can kind of jump here and get X, or I can jump here and take Y, right? So the way I arrange my struct allows me to extract values in a way that memory access cannot do, but it allows me to utilize those 64 bits within the struct in an efficient way, right? So we have to know what the boundaries are. And right now we're talking about the words, but there is another limitation, which are pages, but we will kind of not dive into pages. You probably had pages when you were having the operating system course, but let's focus on words, right? So it kind of matters because it affects performance. It affects how many memory reads will I have to get. So if I arrange it nicely and I have this XYZ situation here, I only need one memory access to get all 3 and do something with it, right? But if I arrange it badly and I have X here, Y here, and Z here, I need 3 memory accesses. So I'm already 3 times slower, right? At least. So it affects performance. It affects how the cache works, right? Because if I align it well, I only need 64 bits. So if I have 10 records, I will have 10 times 64 bits, or let's say it's like, let's operate on words. So 10 one-word situation I would have. So then if my cache is like 16 kilobytes, I will kind of have certain utilization of my cache because I'm doing 10 times one word. But if I align it kind of poorly, I now have 10 times 3 words, and my utilization may hit outside of my possible capacity of the cache. And what I will have to do, I will not be able to use the cache values. I will have to go to memory to fetch the new cache line, right? And using something from the cache and going to memory and fetching something from the cache to fill up the cache line is between 10 to 100 times slower than using the cache, right? So that affects performance massively. So you have to align things properly to reduce the cache miss. What is a cache miss? Cache miss, you need a value that you read before, and it was in the cache, but you ran out of space, and then the CPU had to like fetch new stuff from RAM into cache, and then you try to use the value that was there just a moment ago, but it's not there anymore. And it's called cache miss, because now the CPU says, oh shit, I don't have it. I have to go to RAM and put it into cache again, right? We never read stuff directly from RAM. Like the CPU has to first cache it and then use it from the cache, right? So A cache misses every single time you want something, but you don't have it in the cache, right? And then memory usage, as we said, like we're gonna be wasting memory if we align it wrong. And then we may even have bugs because we aligned it wrong, and on a different architecture, the boundary is in a different place. So it may happen that you have some compatibility considerations. And especially if you're going from 32 to 64 architectures, they have different constraints, right? So unfortunately to you, it used to be fun and like easy. I just need a couple of fields and I don't care about anything. And now if you do a wrong memory alignment, it's a mistake. It's like, oh, you're gonna be punished, right? You have to think how you're aligning your variables and your structs because they influence the rest of the system. So here we said we need A, B, and C. A is unsigned 8-byte integer, unsigned. Then we have a long one, like 64 bits, and then we have a 16. So in total, if you declare this struct, you're gonna use 24 bytes, right? Because this one is 1 byte plus 7 unused because we are using the 64-bit architecture. So we order things by words which are 8 byte each, which is 64, right? So if you think about it, it's like 8 bits times 8, right? So we have 8 slots, 8 bits each. So then we just need one of those slots. So 7 are kind of unused, right? Then we need all 8, which is fine. And then we need half of them. We just need 2. Sorry, we need 16 bits. So we just need 2. And then 6 are padding. We don't use them. So this is very inefficient because it uses up 24. If we reorder them, we start from the biggest, then the next big, and then the small one. We will kind of have this one here. So we will use 8 and then 2 plus 1. So it will be 3. And then we have to have a padding, which we only need 5 for this combination. And in total, we're gonna only use 16, right? So we have quite a nice saving by kind of aligning the 2 small ones kind of next to each other such that they can be combined. So yes, you will have to pay attention how you declare your structs because you have to remember that memory alignment is something that it's on you now. All right, so then we have arrays. Arrays are using square brackets as in many languages. So you remember tuples, round brackets, struct, curly brackets, and then arrays, square brackets. Very similar to lists in Haskell, and I often conceptually make a mistake thinking about arrays as lists and lists as arrays. It's kind of a very similar concept. And then you have a potential size. So you can declare you say, I have a list, I have an array of 10 I32 integers, right? And those are not unsigned, they are normal signed integers. And then this is the size of how big the array is. So arrays have to have a size. You cannot have an arbitrary size array. Same as like in Golang. So this concept is pretty consistent. So arrays are kind of the same as in Golang. And then you have slices, which are also similar to, like there is no example here, but slices are same concept as in Golang, which means I have a slice over an array, and the slice is sort of like the view over a data structure that it kind of, represents. Functions, FN keyword, and then we have anonymous functions. And this is very similar to any lambda. In other languages in C++, those are called lambdas. Here they call them closures. And we have higher order functions. What is a higher order function? is the function that either produces a function or takes function as an argument, right? What is a closure? Okay. A quiz. Oh man, we have 10 questions. So let's see how it goes. How are you ready for Rust? So let's talk a little bit about the closures. Okay, start the quiz. Closures and anonymous functions are the same thing. No, they are not. Very nice. Most people got it right. Half of the class. All right, one more. So I had this, I have this checked with LLMs when GPT-2 was around and GPT-3, and they were doing it wrong. But the latest LLMs are doing it correctly. They learned that, you know, what is what. So hopefully, if you need to interrogate LLM, they will give you a correct answers. Right. So yes, anonymous function is just a function without a name, and it is kind of useful for many languages to have an ability to define a function that does not have a name. Right. In Golang, it's very common. Like in Golang, you often have you can say it's very nice. Golang is quite nice because you can say I have variable f, and variable f is a func which takes an int, right? Like a, and produces an int. And you can kind of do this. So this func doesn't have a name. It's a lambda, but it looks very nice. Like it looks like a normal function, and you assign it to f, right? So like lambda functions and like anonymous functions in Golang are like designed very nicely and very intuitively. All right, so one more. What is a closure? Yes, a closure is a function that captures something from the outside context, right? So let's do Golang. So if I have f, and f is a function that doesn't take any arguments, okay, and returns return 42. I don't need quotes. So now if I call f, it will return a function which does not take any arguments. And so I'm calling this function because f is a variable which is a function. So I'm saying, yeah, like call this function. And then this function returns 42. And this function always returns 42 because it does not capture anything from anything, right? So now if I say, okay, now I have a stupid function which takes an a, which is an int, and I call it with 42, then again, this function doesn't capture anything from outside, from anywhere, because I am passing the 42 as an argument. So this function will always return something based on this argument because it is not dependent on anything elsewhere, right? So this with and without the argument is an anonymous function. and it is not a closure. So to make it into a closure, I could have something like this. I could say if, and then let's say I have a B, which is true, right? And I say if B, then return 42 or return A, else return A times 2, okay? So now, if I call f with 42, it depends, the behavior of the function depends on something outside of this scope, of the scope of the function, right? So this is the scope of my function, but the behavior depends on B, and B is from outside of the scope of the function. So now this is a closure, right? All right. One more. Final question about anonymous functions and closures. Is it true that the closure has to be anonymous function? Of course not. Of course not. And we are using, especially in Haskell, we've been using closures all over the place, and all our functions were actually named. Plus was one of them. We were making closures out of plus a lot of, many times. So no, that's not true. So then we have some people doing pretty well. Yeah, Ellen on the lead. So there is a question about Rust. You will probably not know, so you will have to guess. So in Rust, a named function cannot be a closure. So this is one of those things in Rust which I don't like a lot. So Go versus Rust for anonymous functions and for closures and for high order functions. Like Go is a clear winner in terms of syntax. So in Rust, you cannot make a closure out of named function. And I was like, what? Like, why not? We've been using it in Haskell like all the time. And we can do it in Golang all the time. Like, why not? Okay. So one more. Of course it's false. Yeah, I gave you the answer like on the on the whiteboard. So we're not gonna write kind of examples, but final question about Rust. So when you are learning a new kind of programming language, or when you're learning something new, you have those WTF moments. And it's like, what is going on here, right? So yes, in Rust they call all of them closures. Like, but it is not a closure. It's just an anonymous function. It doesn't capture anything, right? They still call it closure, right? So it's like, okay, what's going on? So why do you think in Rust they violate the semantics of what it means to have an anonymous function, and why they call all the lambdas and all anonymous functions closures, even though some of them are not closures? Why do you think they do it? I still disagree with this. I still think that's a design flaw. But why do they do it this way? Apart from, I don't know. So the reason why they do it is memory management. The compiler has to work out exactly what happens with memory, and closures are complicated because closure captures something from outside of the scope, and then this capturing basically messes up your reasoning about what is allocated and when some things are being released. So they have to err on the side of caution, and they have to say, we don't trust the programmer, and we will treat everything the programmer, she or he, are doing with anonymous functions potentially as closures, because we have to do all this analysis around the memory management, right? So because they have to do it for every single function, even though it is not a closure, they call all of them closures, right? Because the analysis always conducted the same way. They just don't trust that you would be able to know what's the difference between closure and non-closure anonymous function. So they say the programmers will probably not know. So let's treat all of them potentially as closures, even though some of them are not closures, for our memory management, right? Yeah, what are the higher order functions? We already discussed this. It's the function which either takes a function as an argument or produces a function as a result. And here we have a very typical book example from Rust book, where we're doing the sum of squared odd numbers. We've been kind of practicing that a little bit with Haskell, and we can see familiar terms like map. We can see familiar thing like take. We can see familiar thing like filter, and we can see very familiar things like fold. And we can see that we are generating infinite sequence from 0 to infinity. Like, oh, yay, Rust can deal with infinities, with infinite sequences. And we just mapping like a lambda over the values. So we're generating squares, and then we take in a certain amount of those generated squares by this condition that we have. And then we're filtering all the results that we got from here to check if this condition is true. So if they are odd, and then we're folding the whole thing using the addition to do this sum, the final sum. We're using the fold, right? And we can see that the function that we are doing with the fold is very explicit. It basically says what is on the left-hand side and what is on the right-hand side, right? So from this, can you tell which fold is it? Is it the left fold or right fold? So look at this. Think which fold is it, if you can recognize, and then answer. Yeah, we can. Yeah. Very nice. More than half of the class. Perfect. So let's see how we're doing stat-wise. If there is a rotation. Yeah. We have a bit of a rotation of the, but Elin was the first one. Perfect. All right, so let's have a break then. And we have probably like 20 minutes left. I have probably another 20 minutes and then there is a small task. Yeah, so those will hopefully they will kind of set up Rust and Rust up and just get the compiler going and the tests going. So it's a very rudimentary thing, just with cargo and like a small like a loop that they have to do. So that's the lab for today. Yeah. So today is they have to find what is the smallest number that is divisible by numbers 1 to 5. You can do it in your head. And then 1 to 20. That one you cannot do in your head. And that one you also don't want to do with force because it kind of explodes the search. So you have to be a little bit smarter. But they can start with brute force and then they can try to be smarter. Okay?